Resume. So let's talk about the second half part, part B, which is this part is kind of I think new to most of you guys because you have to read a lot of codes. That's basically the challenge, and so for every part B of each project, for part B of each project in the future, we'll always deal with XV6, which is a simpler version of the operating system. And so you can actually compare this XV6 code with the real like Linux operating system code. There's a huge difference because uh, the XV6 is much simpler or easier than the real world Linux or other operating system. So here it's just more like a toy model for you to get familiar with the some ideas of how the operating systems work under the hood. And yeah, so I'm not sure if you guys have the chance to download it, this tar file, and then untar it and take a look at in it yet. So I assume you have already downloaded it somewhere. So for instance, let's go to my version. Okay, so this is the, when you untar it, you will get a bunch of folders and files here. In XV6, I think there is a tutorial for how to run this. So I think I can have a brief demonstration here. So to run the XV6, you can use this command, the make. So the qemu. So what is qemu? Essentially, an emulator provide a virtual environment for the operating system to run on. Okay, so it's kind of emulator. And then this tag no x means no graphic interface, no UI, because basically you want to run it on the CS lab Linux machine, right? And it's not very convenient to manipulate with the graphic every time you have to. So it's basically we will recommend not using the graphic. And even so, even you use the graphic, it's not the graphic. It's actually very ugly, and I don't like it very much. And it doesn't give you much convenience compared to the non-graphic one. And so that's basically this tag. And then that's it. Um, so actually, wait a sec. Before I'm
NOx.
NOx is no graphic.
Okay. And then GDB is.
Oh, GDB is for debugging. I will talk about later. So it's kind of like debugging tool, which is very useful, especially in XV6. You can use GDB to debug your part A.
GDB is equal.
Okay, what is it? Okay, so I think I compile it first, so I just make sure I start from the very beginning. So I will just make clean first, delete a lot of binary files, and now it looks much cleaner. And I'll make qemu nox again. You can see there are a bunch of things happening here. That is compile all the source files in the needed for XV6. And now finally you get a prompt, right? The $sign is actually a share prompt. So here we are entering the XV6 operating system. So it's very similar to Linux. It has got some basic user program. So like the first Linux command or first Linux program you can think of, I think is ls or cd, something like that, right? So you can do similar thing here, but it's very limited. Like it's very basic functionalities. A lot of functions are not implemented in XV6. Okay, so it's just like a toy model. So you can use ls, which is to list all the files in this directory. So you can see there are a lot of files here. So it's kind of like the ls in Linux, but still not the same, not very much the same. So you can also change directory to, I don't think there's a directory here. We can make a directory even. We can make directory like test1, and when you ls again, you'll see test1 here. And you can cd into test1. Okay, what if you type ls here? It says execution failed. Why is that? So it's kind of tricky because you have already changed directory into test1, right? And now ls xv6 does not know what ls is anymore. The reason being that ls is stored in root, which is the home directory. But when you cd change directory into this folder, xv6 can no longer find ls because it's not in the root anymore. So the best way to do that is use this dot dot, means that the parent and ls. Then xv6 will know that, or I can say shell will know that where ls is. Okay, so dot means the current directory, dot dot means the parent. But why can we do ls arbitrarily in Linux? Why don't we write? Why don't we need the exact the path? It's kind of yeah, that's fine. So why don't we need in Linux specify the absolute path? Well, this is kind of well, actually, you can go to. I'll just log in again. So this is the real Linux machine, and when you type which, it will tell you the path of a specific program, which is ls here. It tells you it actually at /bin/ls, and actually we have something called the environment variable, which is at dot dash rc. So it's actually predefined a bunch of paths in this file, and if you define the path here, then Linux will try to look for the program you are issuing from this given paths. So actually, Linux does not know where ls either, as long until you tell them where to find it. Okay, but in xv6, we don't have this advanced functionality, so you have to specify it like the absolute path. But this is kind of side notes. It's not a core issue here. It's just some random thing. Okay, in case you are curious. Okay, so that's basically the kind of the shell demonstration for the xv6. Okay, but okay, another thing is that how do we exit this operating system? How do we exit the QEMU, the emulator? We just use Control A plus X. Sorry, Control X. Oh, excuse me. Control A plus X. Then we exit. Okay, this is a very common command you need to remember. The short.
Control X.
Control A X.
You hold Control and A and then you X.
Right. Actually, you hit Control and A and then type X. Doesn't work.
Finally got it.
Okay. Otherwise, you should directly close the terminal window and relog in again, which is very inconvenient. Okay.
So do you actually say you have to put
Probably it means the graphical terminal. But if we don't use graphical, all you need to do is just use this shortcut keyboard. Okay. Now let's take a look at some some portion of the code here.
So you said you did something where if you no longer got to no longer got SLS.
Mm-hmm.
What step is that? Is that just run?
So make QEMU is just to issue the operating system, and then at root you type ls. That is totally fine because ls is stored in root. You can see here ls is a file here. It's stored here. But if you change directory to test1, which we created just now, then you type ls. It can no longer find it because we're not in the root anymore, and there's no such a mechanism to tell xv6 where to find the ls. This except in the current folder. So that's why we have the issue.
So when you try to see test1, it says you cannot see test1.
Oh, that's because you haven't created yet. Test1 is when you create it. How to create it? You just use make directory. Make directory to create another folder. Okay. 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 Now let's take a look at some portion of the code. I understand at the first sight it looks horrifying because there are a lot of code. So because can you see kernel? There's well, let me make clean because there are a lot of there's still a lot of C code here. Each one does different things. So basically, the structure of xv6, the source code of xv6 can be roughly divided into two parts. The first part is the kernel. The second one is the user. So I'm not sure if Gerard has mentioned that in operating system we have basically two modes. One is the user mode. The other is the kernel mode. He hasn't mentioned it yet, or have it?
He has not mentioned it yet. It was mentioned in 357 though.
Oh, okay, okay. I think he will talk about in great details tomorrow. So it's kind of in advance, but I think I can just briefly talk about the user mode and kernel mode. The reason is that why do we need user mode versus kernel mode? Right, security issue. Because operating system is essentially a software, but it's different than other normal application software in the sense that it can manipulate some of the resources from the computer, like the CPU, memory, disk. It has some access to these resources. However, if the user write a program that can randomly use these resources, then something bad will happen. Right? You can imagine that. Like he can write a program that runs infinitely on this operating system, which does not have this security protection. Probably he's not intended to do that, but probably because of a bug, then the whole system will crash. That's bad. So we have to, in order to prevent or protect the computer, the operating system has to have this different levels so that the user basically lives in the user space. And the operating system takes charge of the kernel space. However, if the user really wants to access some resources in the kernel, how are we going to do that? The simplest example is that the user issued an I/O, which we just now did. Right? Read a file, write a file. This looks very common, right? But it's still actually we have already used the resources, which is the disk, right? So we access these resources, then we have to, but the user cannot, in user space do not have the direct access to these resources. So what do we do? So the operating system grant the temporary access for user to use the resources and then do what it does and then go back to the user mode. So that's basically a vague description of how to transition from the user mode to the kernel mode. And this has got a name, and I've already mentioned that it's called the system call. I think Gerardo will talk in great detail tomorrow. But yeah, so system call is essentially grants user to to use some resources from the kernel. That's basically the idea. Okay, so let's take a brief example of the user first. So just now I mentioned the program like ls, cd, oh no, probably not cd, but basically ls. And I think there are more here, for example, the remove. Right? Remove is to remove a specific file or folder. These programs are just user level program. Okay, so let's take a look at the ls, for instance. So ls is in the user/ls.c. You can see there are, so this is the main function for ls. Okay, sorry, this is the main for ls. It takes in the argument, right? And then call the ls here. And ls will do a bunch of open thing, right? This open is actually just a system call. And fstat is just to read to get the size of the file. So there are a lot of things happening here. Okay, so for simplicity, let's just try to write a simple, very simple user program in x86. Okay, let's call it hello.c, for example. So in x86, the user program is very similar in a sense of what you did in the Linux. So in Linux, you write a C program called hello.s, right? I think it looks very similar. One slight difference is the printf function. So normally you call printf, you write like hello world, and that's it. But for x86, printf is slightly different from what is defined in Linux. You have taken extra argument, which is 1. 1 here is the file descriptor. So still remember, what is the default? What does 1 mean in default as a file descriptor? 0 is standard in, 1 is standard out, 2 is standard error. So basically it means we print this string hello world to standard out. So the printf function in x86 is slightly different. So just remember that. Okay, I think that's it. That's the slightly different here. The include function is slightly different. Let's take a look at ls.c. So you can see ls.c include this thing. So let's just try to copy this. So the include part is also different, slightly different from the Linux. In Linux, we have this right, the smaller than or greater than sign. But here in x86, it's just the quote. Okay, I think that's basically the simplest simplest program in x86. Okay, now let's go back to this file and make QEMU again. Oh, by the way, sorry, I forgot another thing. If you want to add a user program into x86, besides adding the source file in user, you have to do another thing. You have to add in a file called makefile.mk. So here it lists a bunch of user programs, right? This is actually just a make file to tell the compiler that x86 has currently this many user programs. But since we have added another user program, so which is called hello, you should add it here so that the compiler will compile hello.c. Otherwise, hello.c will not be compiled. Okay, so this is the key thing here you should remember. Now we can go to make query new again. Hopefully nothing's wrong. Okay, now let's ls again. See, we have a hello here, which is actually the executable. And now let's try to call hello. We got this. We don't have the new line, so it's kind of not good here, but yeah. So that's basically the simplest user program. We can try to do that. Okay. You mean man page specifically designed for XV6? I don't think so, but there's a called manual for XV6, but it's not like this complete, like it's got a very concrete example and what each tab means. But in XV6 we don't have this, but we do have a manual. I think it's already in a link. Yeah, you can try to look at it. Okay, so this is a very brief introduction for the user program. But for the project we are doing here, we need to write a system call which is called get ppid, right? Now, actually in XV6 there is already a system call called get PID, which is a parent ID of a PID is a process ID of a specific process. You can try to run it to see what does get PID do here. So let's again go to the user and just add it the hello. Now let's just try to do some. Let's just try to call get PID here. Process get PID. So get PID is a function that takes no argument here, and it's a system call, and we can call it from the user. So the idea is again, we cannot. So PID is essentially a field in the PCB of a process, right? The process control block. Did Gerard mention that yet?
A little bit.
A little bit, okay, probably still also tomorrow. So this is just a kind of information to track each process, the information of each process, and this can be treated as a kind of resources. Okay, these resources is like to how we virtualize CPU, right? But this resource is still kind of private to the kernel. What if user wants to get this information, this resource from the kernel? System call, right? So we cannot directly get access to the resource from kernel, but we can do that through system call. Okay, so get PID is just a system call that we can use from user program. And when we call this system call, OS will give us temporary privilege to get access to some specific resource in the kernel, and then we're ready to go. Okay, so this is basically what it does. Now let's try to run it again. Type hello. See, so we have 3, which is the PID of this process. Okay. Okay, now let's take a look at what does get PID do internally. So, because I said get PID is a system call, so it should be defined in the kernel, no longer in the user, because it's not a user program, it's a system call. So it's in the kernel. There is a file called syscall.c. Sorry, not this one. think it's sysproc, sysproc.c. So here it's got a bunch of function. When you search get PID, see we got here. So get PID is a system call, and it's very simple. It just returns proc.pid. What is proc? Proc is essentially just a data structure to hold the PCB, the process control block. Okay. So where is this data structure defined? So there are a lot of kind of tiny things. So probably you should make notes because it takes some time to remember. So where does the PCB define? It's actually in the proc.h, the header file. So it's here. So this chunk is just defining the PCB of a proc. You can see there are a lot of fields, and then I think there's something that is very obvious, right? The size is size of process memory. This is a page table. Page table, we'll talk about it in the second chapter. Kernel stack, probably not now. Okay, see, PID is the process ID. So when we call get PID, we'll just return proc.pid. It's just that simple. And also got a name, process name, something like that. So this is a very short field, a short data structure for PCB, right? If you look at the PCB for Linux, PCB alone, it's got like 100 or 200 lines. So you can see how simple the x86 is. Okay? Then there's a tricky thing is that how are we gonna transit from user mode to kernel mode? And after we finish what we are doing, we'll get back from kernel mode back to user mode. Right? So again, this procedure will be also discussed in a lot of details tomorrow. But now I think I will just talk about it in the perspective of the coding side. Okay, so we also say, I just now mentioned GDB is a great tool a very powerful tool for debugging x86. Now I want to show you how to use GDB using x86. And after that, we'll try to use GDB to take a look at, to trace the code from the user program, how it gets into the kernel mode, and then go back to the user mode. Okay, so that's the plan. Okay, so to start using GDB, all we need to do is just to add the GDB tag after this. Okay. And then you kind of got stuck. So now we need to open another terminal. Make sure you are in the same directory as in the GDB here. Okay. Okay, so you type GDB. Now you are in GDB. But I think for the first time, if you run GDB for the first time in this case, you cannot directly get here. The reason is that you should add something. Okay, now let's, because there's still some learning barrier in using GDB. So because this kernel is completely, I've used a lot. So let me try to switch to a, sorry about that. Let's try to, demos. Let's try to copy let's start from the fresh new x86 code. Okay. So I think it's at it's at TA x86 XE6000. Okay. Now let's just unzip it. 6. Okay, now let's start from here. Okay, so let me copy what we have just now. It's at user hello. Okay. I'll C to user here, and again we need to add in the make file. Make sure that hello is also here, so that the compiler will compile it. Okay. Now let's make sure everything goes correctly. Okay, looks fine. Hello. Oops. That's weird. Wait a sec. Let me take a look at the user. Yeah, I'm not sure. Let's see. Yeah, user as. Let's see. Yeah, it's the same. Oh, I see. So I know the issue. So okay. So every time in XV6, the user program you should exit because there's some fuzzy thing there, but never mind. Just add exit, and I think it will be cleaned up. Now let's make clean and make clean again. Okay, now that looks better. So, and remember to exit at the very end of the main function when you write a user program in XV6. The reason you use exit is because exit actually cleans up something. So, yeah. Okay. Now, if I try to use GDB here, and make sure I navigate to the same directory. Okay, here, let's run GDB here. You'll get something here, the warning. And it says to enable execution of this file, you should add this to the path. Okay, so let's do that. So just add this text into your, so you see, so add this string to your configuration file.
What is it doing?
So it's basically add to tell GDB where it should get started, something like that. It's just like a configuration file for GDB. Okay, not Axis, it's just a configuration
If we
file.
don't see that, we have to worry about it.
You don't see that?
When I type in GDB,
Mm-hmm. Oh no! You should every time you run GDB, you should open at least 2 terminals. For that one, it's just got stuck, and it's actually correspond to this guy. This one's when you type make remove nots GDB, and you will kind of get stuck. Nothing happens here. And at this time, you should open another terminal and navigate to the same directory and type GDB alone. And type GDB alone, and then you will pump through this, and you will find to enable execution of the file, add this to your configuration file. Okay, so let's quit it first. We just add it to. It's actually just in the root called GDB init. And here say, well, I have already added something because I run GDB elsewhere. But for this particular demo, you just need to add another line here. Okay. So you see, I have 4 more paths. That is for the GDB is for somewhere else. But yeah, for this particular demo, you just add this here. And now let's run GDB again. Okay, now we're ready to go. Okay.
Is all of this explained somewhere? I lost you, so it's like that.
I think the GDB usage is not in the course website. If you want to know that, you should Google that yourself. Sorry about that. But can you tell me where did you get lost? So let me take a brief summary here. To run GDB, first you just type this, right? Just add -gdb after the command where you issue the x86. And then you got stuck here, that's fine. And then you open another terminal, navigate to the same folder, and then type GDB. And the first time you type GDB, you will get a warning saying, hey, you should add this string to the configuration file. And then you add this string to the configuration file, and then you run GDB again, then you're ready to go. Okay. So another thing is, okay, because we want to debug from the user program, right? Then you should add something to let GDB know. Another command is you should add symbol file, and then fs, because it's called hello, right? Here, this is a command that you need to use to add your user program hello, so that GDB will know that you are trying to debug this code. Okay, and what does 0 here mean? The hex 0 mean it means it's kind of tricky here, but for in case you are curious, it's just just tells the GDB that you should start from the main function that starts from 0. So don't worry too much about that, but just add this, accept it. Now GDB knows all the symbols, all the functions in the hello.c. Okay, and now let's try to create a breakpoint, right? So let's just break. So break is just set a breakpoint. For simplicity, you can just use b. Okay, it means to set up the breakpoint at hello.c, column followed by the line number. Say I want to track line number 1, and to set up breakpoint line number 1, and that's it. Okay. Now let's just type continue, or you can just use type C for complexity. C means continue, means let's run the program. Yeah, I think we should again. Okay, now okay, probably you should type several times C, continue. And now you can see GDB gets stuck here, continuing, and it gets stuck, it gets hanged. Now let's switch back to the first terminal. You can see the prompt appears, and now you can write something here. Okay, I see. So
Are the instructions for you different for x86 in the arcade, or is this just alternative?
sorry.
Are the instructions like versus B space file name colon I'm wondering. Like, is it just an alternative? Is it the same for Linux? 'Cause
Oh,
I'm used to break and run and like other commands.
mhm.
Are the commands the same?
It's that exactly the same. It's
Okay,
just
so it's just
from
another syntax.
GDB. It's not x86.
Okay.
So this is just
Cool.
perspective of GDB. Yeah. Okay. So I think I probably set a the breakpoint is not correct, not very good because I set up at the main, and so it's every time it hits the breakpoint, it will get. So I think the breakpoint I set up is not very good. So let me do that again. Sorry about that. Okay, let's rerun this and then GDB. Again, I need to add a symbol file. Oh, probably, yeah, I need to add a symbol file. Which is fs hello. Let's just try to break at I think line 6. Okay. Now let's continue. Okay. I'll not type ls again. I'll try to directly call hello, our user program. Okay. Okay, now hello gets stuck. The reason is because we have set up the breakpoint here, right? So you can see it hits breakpoint 1, which is the main function. So line 6 is corresponding to the main function. Okay, now let's type next, which means to step to the next line, you can abbreviate as n for next. Now line 7, right? And it says printf blah blah blah. Okay, now because this program is very short, right? If we type next again, it just ends. But right now we want to step into the get PID, right? The way to do that, you should not use next. So every time you type next, it means the code will run to the next line for this program. But because it's not next line, it's here, so we should use step. Okay. S for step means step into the function here. Step again. Sorry, I think. Step. Okay, so when we step, now we actually steps into the get PID, and you can see it says this guy. Now it's at user/uc_s. So what does .s mean? What's this file? Anyone has an idea? From 354. What does .s file mean? Right. So it's actually a code. It's an assembly code. So how many of you are familiar with assembly code? Okay. If you are not a trouble, but you have to learn again because assembly code. I think you should know, remember some basic operations or some basic like the move, push, pop, something like that. So let me just open the third window here, third terminal, because I want to look at the code itself. So let me go to demos. This is 6. So it says we are now at user ucsys.s, right? So let's run it. Oh, sorry. User ucsys.s. So it's just a bunch of assembly code. And because we are calling the get PID, so get PID is here. Right, so the line 28, which is corresponding to here, right? Now we are here. And every time you call system call, you will get a corresponding system call number. So I think get PID has a specific number assigned to it. I think it's stored in EX. So you can print info register to inspect the value of the register. So EX is the register. So right now it's 0. That's totally fine. Okay, never mind. Let's just keep going to step into this function. Okay, now it seems that we are in another file, right? Kernel vectors.s. So let's go to here, kernel vector.s. So it's another assembly code, and it's at line 320. Oh, sorry. So it's here. So what does the $64? What does $sign assembly mean?
Immediate value.
Yeah, it
And
means
immediate value means actually a number, not any sort of memory location.
yeah, exactly. So, and what does push L mean?
The L at the end is kind of a little convention in assembly land, they like to add a little letter for certain operations, not all of them, it's inconsistent. That says like this is a long or this is a quad or whatever, which are sizes of data.
We don't care about the
Yes.
type first.
Push in general is a common operation. Means push onto the stack. I'm not derping.
Exactly. So basically, we are dealing with a stack in the memory. So we basically push this value 64 to the stack. That's basically what this operation means. So anyone has an idea why it's 64? So I think it's still, we'll cover it tomorrow. But so I'll just tell you the answer. So 64 is kind of like a magic number in x86. It just means the system call. So every time you issue a system call, you just corresponds to the number of 64. So x86 knows that, okay, now it's 64, it means system call. I'll do whatever system call will do, something like that. So it's just like a magic number, okay? But I think in a Linux system, this system call number is 80. I'm not quite sure. So it's kind of different convention. But in x86, every time you see 64 here, it just means we're issuing a system call. And you can actually go back to usys.s. Here, this command, line number 8. So again, you know, what does int mean here? In assembly, not in C. That's an idea. So it's kind of tricky here. Exactly. So don't get confused. Int here it does not mean the integer type in C. It means interrupt. So this command just means, this instruction means we'll interrupt the system with this number. So if you can search pieces call, okay, so you can see it's defined in include traps.h. So here it's defined here. System, this is a macro, right? T underscore syscall is a macro defined here. It's just 64. So it just means a system call. And we have other interrupt. Not only just 64, we have like the timer interrupt. I think it's here, right? This is the timer interrupt. So what is timer interrupt? It will also be talked about tomorrow. Okay, just leave it for tomorrow. And we'll have a bunch of other macros. So as long as the system sees this number, it will basically jump from user mode to the kernel mode. System call is just one of them. Okay. So another easy case is that when your program does some malicious things, bad things, system doesn't allow it. It will still the program will throw an error. Most of the time, like seg fault, right? And as long as seg fault gets caught, some particular macro, I think it's 14 here, page fault. Yeah, 14 will be reported to the system, and the system you will jump from user mode to kernel mode, and then the kernel will just kill this program. So more details tomorrow. Okay, sorry about that. But okay, so right now we are issuing a system call with a number of 64. Do you have a question? Mm-hmm. Okay, that's fine. So where are we? Okay, so basically we just push this number into the stack. That's what we do here. Now, next step. Okay, so next step we will jump to all traps, which is another, I think it's another assembly code. Now we are in all traps, which is defined here in kernel trap ASM. So this is another, sorry, I know it's intensive, but yeah, soon, almost there. So this is just another assembly code that we are jumping into. This code essentially just deals with how we're gonna handle the registers. Because as you can remember, we are transitioning from the user mode to kernel mode. We have to store something, store information, right? Because if we don't store some information, how are we gonna make sure that we can get back to the correct?
Thanks for using WebEx. Visit our website at www.webex.com.
Okay. Did I say something
the phone
that
was on the entire time? I don't know what that means.
Okay. Okay, never mind.
But
Okay.
probably someone hung up a long time ago. I wouldn't be worried.
Okay. So every time we jump from the user mode to kernel mode, we have to store something. Otherwise, we will have no idea where we are when we get back, right? So here is what it does. So the information I mentioned is basically just a bunch of registers. So we should store some registers for a particular process into the kernel. And then when we get back from kernel mode to user mode, we'll restore those registers so that we know where we are. Okay, so here a bunch of things we just, how to store the registers, we just push them to stack, to the kernel stack. And then we do a bunch of things. And then so for this chunk of code, we are basically call trap. It means that we will deal specific the real thing, the like get PID or get PID here. After we get PID, here we just return from trap after we restore the registers we stored previously. Okay, and now finally we just return from trap from kernel to user mode. So that's basically the workflow. I know it's kind of like confusing, but if you'd like, you can also refer to the textbook, OStack book. So I think, yeah, tomorrow we'll talk about, Gerard will talk about the mechanism for how to switch from user mode to kernel mode and vice versa. So I think it's in chapter 6. So here, the mechanism, this is a very important chapter and also a lot of interesting thing happening, but also a very confusing thing happening here. And here is basically the workflow for how we're going to deal with the system call. So, see, so the program user just call system call, and then we'll trap into the operating system. And then with some help of hardware, which I haven't mentioned it, let's just skip it for now, we'll directly trap into the operating system. And then operating system will handle the trap, do the work of system call, and then return from trap, and then with some help of hardware, and then we just return to the user program. So this is basically how we are transitioning from the user mode to the kernel mode. That's the basic workflow, but the details, leave it to tomorrow, okay? And just now I mentioned, before we jump into the kernel mode, we have to store the registers, which happens here, right? And after we return, we'll restore the registers from the kernel stack so that we know where we should return. Okay, that's basically the idea. And so this just corresponds to, so we just push a bunch of registers into stack. And then we will call track. Now let's go to this line to see what happens here. Another useful, I don't remember the lines, 25? Okay, 25. So in GDB, we can use until command, like 25. We'll just go directly to skip 10 to 24. We just go directly to 25. We can use until short for u. It takes a while. That's weird. Probably we cannot use until in assembly. I'm not quite sure. Never mind. Yeah. Okay. Sorry. I think I should. Okay, let's just call hello. Sorry. Okay, now let's just call hello again. Okay, now we are in get PID and we should step. Okay, here we go. Now we continue step into, here we push the number 64, which is the number representing the system call, to stack. And then we jump to all traps, which is here, right? Let me just step by step. 25. Okay, now we are in 25, line 25. We'll call trap. It just corresponds to this one, the handle trap, and do the work of system call. Let's step. Okay, now you can see we are at another file. Finally, we are not in assembly, we are in the C code. Okay, let's go and see the C code here in the trap. So this is also a very important portion of the operating system. It's just basically a trap handler. So to summarize, when will the user program will get trapped into the operating system? One thing is, as I mentioned, we can issue system call, right? And then user will get trapped into the kernel stack. Another thing is also I mentioned some bugs happen, errors happen. Then the user mode will get trapped to the kernel mode and kill the program. So in the trap.c, you can see each condition or scenario corresponds to a macro or corresponds to an integer, which was defined in just now show you, right? Which is defined in include traps storage. So here is a bunch of macros. So each macro corresponds to an integer so that we know what we will do after we get trapped. So here you can see if the trap number is the system call, which is 64, then we'll do this bunch of things. Otherwise, this corresponds to the timer interrupt. We'll do this. Yeah, a lot of cases. And here we are dealing with some errors, like some error happening. We'll just try to kill the process. So this is basically what the traps is doing. And here, yeah, I think this is more corresponding to the schedule issue. I'll just skip it for now. But now we're just doing the demonstration for the system call, so we'll just focus on this portion. Okay, so now we jump into the line 37, right, which is here. Okay, that's fine. Let's continue. We can use next here because we don't run code assembly now, or we don't step into here. So you can see the trap number. Oops. Yeah. Okay. Let me set up another breakpoint for get PID. Yeah, because this is not the system call here. It's kind of interrupted by the timer interrupt. Okay. So I don't think this is very good way to show you using GDB because there's a bad thing for GDB to debug in this part is that because just now I mentioned traps can happen from issuing system call or errors, or another important portion is the timer interrupt, which is guarantee that each process cannot run forever. It will basically schedule process A for like one time slice, and then we should change to like process B, something like that. This is from the mechanism of the timer interrupt, which was also talked about tomorrow. So, but here GDB sometimes will get trapped not by the system call, but by the timer interrupt, which is not very controllable. So I don't think I will continue doing this, showing this in GDB. Instead, I'll just directly show you the code here. So right now, we say that we are in a trap, right? We'll say if the trap number is system call. Okay, so we are issuing the system call, which is get PID. Now we're in this if statement. And you can see here, we'll call syscall. So this function, in fact, I can set up a breakpoint at 41. And then we can make sure that the GDB falls into 41. Okay, let me do that again. Break syscall. Okay. Now we are in the syscall, which is at kernel syscall.c. Also take a look at kernel syscall.c at line 115. So this is the system call from the trap. You can see we just get the number from the EX, which is the register. What is this number for? Anyone has an idea? Let's see what is num, right? What is you can, okay, in GDB you can print something like print, but you can just short for P, print num. This is 6. So why it's 6? So as just now I mentioned, there are multiple system calls, right? Read, write, open, or get PID. So each system call will get assigned to a number. So here, 6 is a number that is assigned to the system call. I think 6 here is not the get PID system call. It should correspond to write. The reason why do we have call write here? Because we want to print something here. Because right, as long as you print something under the hood, it's just issuing the system call of write. So here we just have the write system call. So you can go on next page. Step into this syscalls. Right. You are now in the. Okay, so it's read. Sorry, read write. Yeah, in the syscall. So let me just set up another breakpoint called sysgetPinfo. Oh, sorry, get PID. Okay. Now I think we are at. What? Sorry, let me. I think it's confused here. Let me just, let me just break sysgetPID. Okay. And we need to add symbol file. Okay, let's run it. Now we should say hello. Okay. Now we are in sysgetPID. Again, it's just a very simple function, right? It just returns the field PID of the PCB. So let's continue. And now after we call get PID, we will just return to kernel syscall 123, which is here. We reach the end of the syscall. And after we return from syscall, where do we get? We should get back to trap, right? Because trap calls syscall. Let's see. Next. Right. Now we're at trap. Right? Kernel trap.c. And we return. After we return from trap, where do we get? All traps, right? Because all traps call trap. Do you still remember? So let me take a look at kernel trap asm.s. So here, right, we were here, call trap, and we are in trap, and trap calls syscall, right? And syscall choose the number of get PID, and then we run get PID. After we get that result, we'll get back, and we return from trap here. And then we continue here we just restore a bunch of registers we restored previously, right? And then finally we return to the user mode. So that's basically the whole process. Next. Finally we return, see, return from trap, and finally we get back to main, which is user hello.c. And we have finished the printf. And you can go back to the terminal, you can see this gets printed. Okay? So that's basically not a well-defined demo, but hopefully you can get some sense of how does user mode gets trapped to the kernel mode, and finally we get back to the user mode. So I think on a conceptual level, it's just this diagram, okay? And it will be carefully taught by Gerard. He will spend at least half an hour or even 1 hour to talk about this, I guess. Yeah. So if you get confused, don't worry about it. Tomorrow, I think hopefully you can get a better idea. And the reason why I spent so much time on this is because in the first project, we are just writing our own or new system call in x86, right? So you have to try to have an idea of how the system call happens under the hood. But actually, in terms of coding, you don't need to write too much things. It's very simple. It's actually, you can just learn how getPID is written and just follow what PID is written and basically copy most of the code from getPID, and then you get, I think, you're totally fine after that. So, but even so, you still should have some ideas of why it happens and how it happens, and then you should not treat it as a black box, right? You should have some idea inside of what happens under the hood. So that's basically this demo. Hopefully you